we need to learn more about Kepler's third law. So, Kepler's first law is that planets orbit the sun in ellipses. Kepler's second law is that planets move faster when they're near the sun and slower farther away. Kepler's third law is a relationship between the total amount of time it takes an object to orbit around the sun and the semi-major axis of the orbit, of the object's average distance from the sun. And Kepler's third law says that p squared equals a cubed. And here p is going to be in years. So in years, that's the number of years it takes an object to make one complete orbit around the sun. And a is going to be the object's average distance from the sun. And we measure this in AU. Now, Kepler's third law applies to all objects which orbit around our sun, and only our sun. So it applies to all the planets, which was what Kepler was studying. It also applies to the comets. It applies to asteroids. It applies to everything orbiting our sun. It doesn't apply to anything orbiting anything else, at least not directly. It doesn't apply to the moon orbiting the Earth, or Jupiter's moons orbiting Jupiter, or the sun orbiting around the galaxy, or anything like that. Kepler's third law applies directly to things orbiting around our sun. All comets, all asteroids, all planets, any space probe orbiting around our sun, this works for it. So what it says is if you take the amount of time, the period of time it takes to make one complete orbit around the sun, and you take the semi-major axis of the orbit, the average distance from the sun, that if you square this number, the years, you square the years, you'll get the same number as if you cube the distance from the sun. Let's do an example. We'll do the simplest example. Let's do the Earth. Well, let's see. How long does it take the Earth to orbit around the sun? 1 year. I mean, that's the definition of a year. So if I take 1 year and I square it, I should get the same thing as if I take the object this well. How far is the Earth from the sun? The Earth is 1 AU from the sun. Again, by definition, that's what an AU is. It's the average distance from the Earth to the sun. So that's going to be 1. And so if I take the period, 1 year, and I square it, and 1 AU, and I cube it, I should get the same number. Well, does it? Yeah, because 1 squared is 1 times 1. What is 1 cubed? Well, that's 1 times 1 times 1, and yeah, 1 equals 1. Are you impressed? Probably not. That's kind of a boring, trivial example. Let's do a real one. Let's do an interesting example. Kepler did his greatest work studying the planet Mars. So let's do Mars. All right, so how long does it take Mars to orbit around the sun? Let's see. It takes Mars, if I look this up, it takes Mars 1.88 years to make one orbit around the sun. Every 1.88 years, Mars orbits around the sun. So if I take 1.88 years and I square it, what do I get? Well, let's see. I'll grab my trusty calculator here. 1.88 squared is 3.5. And if, on the other hand, if I take, well, how far is Mars from the sun? So this is p squared right there. If I take a cubed, Mars is an average of 1.52 AU from the sun. So if I do 1.52 cubed, what do I get there? Well, 1.52 cubed is, look at that, it's 3.5 in both cases. 1.88 years squared is 3.5. 1.52 AU cubed is also 3.5. And there we go. This is the magic of Kepler's third law, and it works for all the planets. If I took the period of time it took for Jupiter to orbit the sun and squared it, I would get the same number if I took Jupiter's average distance from the sun and cube it. It applies to all comets, all asteroids, all planets, everything that orbits around our sun. P squared equals A cubed. Wonderful. Now, how do I use this? I mean, this is a beautiful, wonderful, powerful mathematical law. This says that P squared equals A cubed for all objects orbiting around our sun. So if I give you one of these two things, you can use that equation and calculate the other one. So, for instance, I don't know, suppose I find an asteroid out there, and I find the asteroid orbits around the sun once every 4 years. I could then ask you, well, how far is that asteroid from the sun? Say the orbit of the asteroid is pretty close to a perfect circle, and so the semi-major axis is the distance from the sun to the asteroid. What would that have to be? Well, I go to this equation, I got the P, I need the A, so we just do a smidgen of algebra. I want the A not cubed, I just want the A, so I raise everything to the 1/3 power to cancel out that cube. And so what this says is A equals P to the 2/3. 1/3 of 3 gets it down to 1, 2/3 of, there it is. So it says if I take the period of orbit and I raise it to the 2/3 power, that will tell me the semi-major axis of the orbit. Let's do it. Okay, so this is 4 years is what I said. Let's raise 4 to the 2/3 power. So I go to my trusty calculator, I take 4 and I raise it to the 0.6666 power, and what do I get? It says 2.5. So that means 2.5 AU must be it. That means that asteroid or any object that orbits around the sun once every 4 years must be a distance of 2.5 AU from the sun, on average. The average of the greatest distance and the smallest distance is the semi-major axis, 2.5 AU. Given the period, you can calculate that. Let's go the other way. What if instead of giving you the period and asking you for the semi-major axis, we do the other way? What if I give you the semi-major axis? Suppose there's a comet out there, and the comet has a huge semi-major axis. There are lots of comets that do this. Start up very far from the sun, whipping close to the sun, go far from the sun again. Suppose I've got a comet, and the semi-major axis of the orbit is 100 AU. So it's going to be really far away from the sun a lot of the time. So how much time would this take to make one orbit? Let's calculate it again. P squared equals A cubed. That's Kepler's third law. I want to solve for the P, so now we raise everything to the 1/2 power. I got P equals A to the 3/2 power. And so I can just take that thing in and raise it to the 3/2 power. 100 to the 3/2 power. 3/2 is 1.5, so I do 100 to the 1.5. And what do I get? I get 1,000. And so, cool. So that tells me if I got a comet that's out there so far away that it's at a semi-major axis of 100 AU from the sun, that means it will orbit around the sun once every 1,000 years. Check it out, once every 1,000 years. And so this allows me to then calculate the period from the semi-major axis, or the semi-major axis from the period. And so, but what if I just give you more basic orbital information? What if I do something like this? What if I say, all right, I got an asteroid that orbits around the sun, and here's our friend Mr. Sun. He's at one of the focus points, and I say when this comet is at its closest point to the sun, suppose it's 1 AU from the sun. And then when it's out at its farthest distance from the sun, suppose it's 9. Oops, let me make that better. Suppose it's 9 AU from the sun. And then I say, well, what's the orbital period of that crazy thing? Well, based on this information, we can calculate the semi-major axis and then figure out the orbital period. So semi-major axis is half of the major axis, which means if I take the average of the closest approach to the sun and the farthest distance away from the sun, I get the semi-major axis. So let's do that. The average of 1 and 9, 1 plus 9 divided by 2, 1 plus 9 is 10. 10 divided by 2 is a little number I like to call 5. And so that means the semi-major axis of this orbit is 5 AU. Now I want to know, well, how long does it take this thing to orbit around the sun? Well, again, P equals A to the 3/2 power. We just did one of those, so let's do that again. So if I take 5 to the 3/2 power, again to the trusty calculator, 5 to the 1.5, I get 11.2 equals 11.2 years. So that means this comet with this orbit orbits the sun every 11.2 years. Now here's another cool thing that comes out of this. All that matters is the semi-major axis of the orbit. So there's my comet. It gets close to the sun, 1 AU, far from the sun, 9 AU. Now imagine there's something else. Suppose there's an asteroid that orbits around the sun that is always 5 AU from the sun. And I can't draw a circle, but suppose this is a circle centered on the sun at 5 AU. Well, how long would this thing take to orbit the sun? Again, we can use Kepler's third law, and you notice it's going to be exactly the same thing, even though these two orbits are very different. The one goes from 1 AU to the sun to 9 AU from the sun, and this one is just always 5 AU from the sun. Kepler's third law says it doesn't matter. All that matters is what the semi-major axis of the orbit is. So if it's a circle and is always 5 AU from the sun, well, that's the semi-major axis. A equals 5 AU. So by the stuff over here, it's going to orbit every 11.2 years. So even though these are two very different orbits, one is a circle with a radius of 5 AU, one is an ellipse coming in 1 AU and 9 AU from the sun, but in both cases, they're going to orbit in exactly the same amount of time. They'll orbit in exactly 11.2 years, because both of them have a semi-major axis of 5 AU. And that's how we use Kepler's third law to understand the orbits of everything that orbits around our sun.